that the following are equivalent. In other words, f is conservative implies f is path independent. F path independent implies that the integral over a closed curve, any closed curve in C is 0. What's a closed curve? Yeah, the same starting and ending points. And if we add the precondition n equals 3 and u is simply connected, which basically means that any loop inside the space can be smoothly deformed to a point. There's nothing to catch loops on as you deform them to points. I'll give you more. We'll have a longer discussion of what simply connected means some other day. But if you have these two things, n equals 3 because the curl only makes sense if n equals to 3, simply connected because that's a necessary condition for this to be equivalent, then we get the converse direction to, it's sufficient that the curl of f be 0 on a simply connected subset in n equals 3. That does in fact imply that a potential function exists. So we want to prove this theorem. I would expect that you'd be able to prove this theorem on the next test, for example. So let's start with 1 implies 2. How do you prove 1 implies 2? So assume that f is equal to the gradient of a potential function, right? Let C1 and C2 be curves in U going from P1 to P2, right? And then we calculate the integral along C and so calculate. So integral along C1 of f dot dr is what? Yes. It's this, right? And then that's what? This is equal to f of P2 minus f of P1, right? By fundamental theorem of calculus for line integrals. But by the same token, that's the integral along C2 of the gradient of f dot dr, right? So that's the integral along C2 of f dot dr. Is there a question? Any questions about this part? Okay. So if you want to prove 4 things are equivalent, one nice way to do it is you take 1, you show that implies 2, right? You show that implies 3. You show 3 implies 4. And then if you can show that 4 implies 1, that gives you the logical equivalence between these. Right? This is a logical way of establishing this is true if and only if this, 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 that these are equivalent statements. So we're going to keep working our way down. Let's try to prove 2 implies 3. So assume 2 is true. How will we show 3 is true? There's some pictures missing in my notes here, so I hope you will draw the pictures I'm writing on the board today. So what do we need? We're assuming f is path independent. We want to show the integral around a loop. And so I'm going to be a little bit less adventurous than Sam. I'm going to replace closed curves with a loop, if you don't mind, which I'm just going to assume there's no self-intersection, just to keep things a little bit less cluttered. Maybe that doesn't. Anyway, I'm just to keep things simple. 2, assume path independence of f. Consider a loop in U. So we can picture it like this. Here's my U, whatever that is. My loop is something like that. I don't know what it is exactly, but it's a closed curve, right? My point, Sam, was I could have a closed curve that looks like this. I don't know. I just am nervous about it. So it might not change the argument. Let's finish the argument before we make it way more complicated. So consider a loop, right? In U, what can you do with any loop? Pick a point, right? Pick a point, any point. Say P1. Pick another point, any point. Let's say P2. Not the same point. Then what do? How about this? This up here, I can call C1. Let me call the loop. Let me call it L.
And then do the other path, and then since they're indifferent, then you flip one of them.
Right. I can look at this other path here like that. Let's call it C2. Then L is what? It's C1 union with minus C2, right? See, because so L the loop is, I really should tell you the orientation. The loop is oriented like this. So the loop is, let's see here, clockwise. I'm looking at a clockwise oriented loop. I did. I mean, you could orient it otherwise, but yeah.
Why didn't you make the orientation of C2 the other direction?
So the point is C1 and C2 have the same sort of difference.
See, because C1 and C2 both go from P1 into P2. So we get the integral from C1 of f dot dr is equal to the integral along C2 of f dot dr, right?
Oh, okay. And then you can...
So this is the integral of f dot dr of C1 minus the integral of f dot dr of C2 is equal to 0. But this is the integral over C1 union with minus C2 of f dot dr, right, is equal to 0, aka the integral along the loop of f dot dr is equal to 0.
Okay. See, I was going to start the other way and make negative C2 equal to positive C2 and work backwards.
That would be, yeah, that'd be equivalent. I mean, it'd be same song and dance. That's fine. You could do that.
That argument still works with the cross.
It should.
All right, so next step here. I'm actually, I mean, I advertised this, but it's not entirely generate. I wasn't being, I'm not entirely accurate. The more interesting, this isn't actually logically what I do in the notes. So we just proved 1 implies 2. We just proved 2 implies 3. Those weren't that hard. I'm now going to try to show you something a little bit more difficult, which is that we've also showed, we have established before that 1 implies 4. Because that was that the curl of the gradient was 0. So this is f equals to the gradient of little f, right? But then the curl, this number 4 is basically just that the curl of f is 0, right? So this identity gets you from 1 to 4. We have that also. The direct proof 3 implies 4 seems awkward to me at this point in the course. So I'm gonna kind of stay away from that. And what I want to show you now, and this is really one of the more beautiful arguments that I'll share with you this semester, is that 3 implies 1. This is our next discussion. So we're going to assume, I said 3, I meant 2. Sorry about that. So I'd like to show you that 2 implies 1. This is actually really important to physics because this is how we construct potential energy functions from a given force field. This proof I'm showing you has within it an important construction in physics.
This set of truths doesn't actually give us logical equivalence, right?
Yeah, I'm not. It's a good question. Is if the notes are actually logically complete here. I'm not sure yet. I mean, we're chipping away at it, but there's more to do, for sure.
I mean, at least with what you're drawing here, it's not. But I don't know if you can more than that.
So assume that f is path independent. And we'll work in n equals to 2 to keep things a little bit simple. And we'll let f equal to pq just to keep things really explicit here for a minute. All right? So I have to define f of xy. And here's what I'm going to define it to be. I'm going to say it's the integral from some base point, let's say p naught, all right, to xy of f dot dr. So here's my definition. What do I mean by this notation? Here's a more sort of verbose version of it. C f dot dr, where C is a path from p naught, which is fixed. It's a fixed point in U, to xy. So path independent on U. And this point, which containing p naught. So p naught's a point in U. So this is the definition of the potential. Well, it's not the potential energy, right? Because there's the minus missing. So in physics, what do? You stick a minus here to get the energy. Now, what do we need to show to prove that 2 implies 1? What's required of us? If this is our definition, what do we need to demonstrate? What's our goal? We want to show that the gradient of f is equal to pq.
So we take the gradient of both sides, and then
Yeah, I mean, if you just try to straight differentiate it, it's not going to make sense. So what this requires us to do is to choose some special path. I mean, first of all, this makes sense because of path independence, right? It doesn't matter which path you pick in U, right? As I go from the point p naught, wherever that is, the point xy, wherever that is, it doesn't matter if I do this one, or if I do this one, or if I do this one. They all give me the same work.
we pick a line.
If I picked a line, it'd be the same. So we're going to have to pick a special path which allows us to take the partial derivative. All right? And we'll do that tomorrow because we're out of time. So, thanks, guys.